You are lying in a dark room. The walls are solid. The air is still. Your body feels contained, bounded, separate from the space around you. But that feeling is an illusion. Right now, as you lie there, particles are passing through the walls of the room, through the air, through your skin, through your chest, through the core of your body. They do not slow down. They do not leave a mark. They are completely invisible, completely silent, and they have been doing this since the moment you were born. These particles are not arriving from some distant source. They are here, in this room, streaming through you at this very moment. They are part of the scaffolding that holds the galaxies together. They are the dominant form of matter in the universe, and we have no idea what they are. 85% of the matter in the universe is invisible. We can map it, we can weigh it. We have no idea what it is. Hello, and welcome to Sidereal. Tonight we are going to spend some time with the largest missing thing in physics, the matter that outweighs everything we can see by more than 5 to 1, and which, after 90 years of looking, we have never once held in our hands. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps the channel. And I am always curious where you are listening from, so if you feel like it, drop your location and the time where you are into the comments. Then, settle in. There is no rush tonight. There are a few questions underneath everything we are going to follow. Why does a galaxy spin as though it weighed far more than its stars? How do you take a photograph of something that gives off no light at all? Why have the most sensitive detectors ever built, buried under kilometers of rock, waited years in perfect silence and caught nothing? And why, in the last few years, has the model that was supposed to explain all of this quietly begun to come apart at the seams? We will get to all of it, but we begin with a single number because the whole story grows out of it. 5%, that is the fraction of the universe we actually understand. Everything we can see, touch, measure, and name, every star, every planet, every galaxy, every cloud of gas, every atom in your body, every photon of light that has ever entered a human eye adds up to about 5% of the total contents of the cosmos. The other 95% is unaccounted for. Of that remainder, a little more than a quarter is what we call dark matter. The rest, the largest slice of all, is something we call dark energy. Those are not explanations. They are names we have given to our own ignorance, polite labels stapled onto two things we cannot see and cannot describe. We use them the way a mapmaker once wrote here, be dragons, across the blank part of the chart. The words mark the edge of what is known. Tuzo. 2. It is worth being clear about how confident those proportions are, because they sound like the kind of thing that might be loosely guessed at, and they are not. They come from several completely independent lines of evidence that have no reason to agree and do anyway. The pattern in the oldest light in the sky gives one measurement of the recipe. The way galaxies are spread across the cosmos gives another. The abundances of the lightest elements, cooked in the first few minutes after the Big Bang, give a third. The brightness of distant exploding stars gives a fourth. Each of these is a separate window onto the contents of the universe. And when you ask each of them how much ordinary matter, how much dark matter, how much dark energy, they hand back the same answer within a few percent. 5, 27, 68. The numbers are not a guess. They are one of the most thoroughly cross-checked results in all of science, which only makes the situation stranger. We have measured the proportions of the universe with great care, and 95% of what we measured is something we cannot name. And notice what falls inside that thin 5%. Not just the things that glow, everything you have ever encountered, every element on the periodic table, every living thing that has existed, the Earth, the Sun, the planets, every star you can see and every star you cannot, all the gas drifting between them, every atom that has ever been part of anything, the entire visible, tangible, knowable cosmos, all of recorded human experience of matter, fits inside the small, bright sliver. The rest is the part we are here to talk about. Dark matter is the part of that darkness that behaves like ordinary mass. It pulls, it has weight, it bends the paths of stars and the paths of light, and it is not confined to some far corner of space. It is everywhere. It is here, In this room, by the most careful estimates, it is passing through your body as you listen. It is worth keeping the two darknesses separate in your mind, because they could hardly be more different. And tonight, we are concerned mostly with one of them. Dark energy, the larger slice, is not matter at all through Mafel and does not clump or pull. It is a kind of pressure woven into empty space itself, and its effect is to push the universe apart, to make the expansion of the cosmos speed up rather than slow down. It works on the very largest scales, and is, if anything, even less understood than its companion. Dark matter is the opposite kind of stranger. It gathers, it pulls things together, it builds. Where dark energy spreads the universe thin, dark matter is the reason there is any structure in it at all. The reason matter ever clumped into galaxies and stars instead of drifting apart forever. The two of them, between them, make up almost everything, and we can name neither. But it is the gathering one, the building one, the one that is in this room with you, that this story is about. The dark matter belonging to our own galaxy forms a vast, roughly spherical cloud, a halo that the bright disk of the Milky Way sits inside, like a coin dropped into the middle of a beach ball. That halo is something like 1 million light-years across, and it contains the great majority of the galaxy's mass. The stars, the gas, the dust, the spiral arms we photograph and put on posters, all of that is a thin glowing residue suspended inside something far larger and entirely invisible. The solar system rides through this halo. The Earth plows through it. You are inside it now, and it is inside you. The density of it, here, in the neighbourhood of the Sun, is very low, roughly 1 proton's worth of mass for every few cubic centimetres of space. That sounds like almost nothing, and locally it is almost nothing. But space is enormous, and the almost nothing is everywhere, and it adds up. Add it across the whole volume of the Earth and you get, at any given instant, something like 1 kilogram of dark matter threaded invisibly through the rock and the oceans and the core, drifting through all of it as though the planet were not there. And the number passing through a human body each second is, by any honest reckoning, in the billions. You cannot feel any of it. You cannot see it or hear it or taste it. It interacts with ordinary matter so weakly that it leaves no trace at all. It goes through the Earth as if the Earth were a window. It goes through you as if you were a window. This is genuinely hard to picture, because nothing in ordinary life prepares you for a substance that is both everywhere and untouchable. We are used to things being either present or absent. The wall is solid, the air is thin, the space across the room is empty. Dark matter belongs to none of those categories. It is present in the sense that it has real mass and real gravity, and is, by weight, most of the matter around you. And it is absent in the sense that you could swing your hand through a cloud of it or walk through a wall of it and feel nothing whatsoever, because it does not push, does not resist, does not warm or cool the skin, does not register on any sense you possess or any instrument that works by touch or light. It is matter that has been stripped of every property except weight. The only thing it does is pull, gently, with its gravity, on everything around it, and that single faint property, multiplied across the whole universe, turns out to be enough to build galaxies. And yet we are certain it exists, not because we have caught it, but because we can see what it does. Without it, the galaxies would fly apart. Without it, the structure of the cosmos, the long luminous filaments, the clusters, the great walls of galaxies stretched across the sky would never have formed at all. Without it, in the most literal sense, there would be no stars, no planets, and no one lying in a dark room thinking about any of this. That is the strange shape of the problem. We know dark matter is real with about as much confidence as we know anything in science, and we have not the faintest idea what it is made of. The story of how we arrived at that contradiction is almost 100 years long. It runs through a difficult, brilliant man arguing with a swarm of galaxies that refuse to behave, through a quiet woman at a telescope who watched the same impossible thing happen, galaxy after galaxy, and reported it without raising her voice, through 40 years of detectors lowered into mines, and 40 years of silence coming back up. And it ends for now not with an answer, but with the unsettling sense that the silence itself is trying to tell us something. So we start where the silence started, In 1933, on a mountain in California, with a man looking at a cluster of galaxies that was moving far too fast. His name was Fritz Zwicky, and almost everyone who worked with him found him difficult. He was born in Bulgaria in 1898 to a Swiss family, and he kept his Swiss citizenship his whole life. He trained in Zurich and then crossed the Atlantic to the California Institute of Technology, where he spent the rest of his career. He was abrasive, certain, and openly contemptuous of colleagues he judged to be unimaginative, which was most of them. He is supposed to have called the astronomers he disliked spherical bastards, he explained, when looked at from any direction at all. He made enemies the way other people make small talk. He was also one of the most original minds of his century, and a remarkable amount of what he proposed turned out to be correct decades before anyone could prove it. Just a year after the work we are about to follow, he and Walter Baade coined the word supernova, and proposed correctly and seemingly out of nowhere that the collapsed cores left behind by such explosions would be stars made of packed neutrons. The neutron had been discovered barely 2 years earlier. Almost no one took the idea seriously. It took more than 30 years and the accidental discovery of pulsars to prove him right. Zwicky had a habit of being right early and being ignored for it, and the story of dark matter is the largest example. He worked, by temperament, the way a prospector works, turning over enormous quantities of material in the hope of the occasional nugget, and trusting his own judgment over anyone else's about where to dig. Over his career, he personally discovered well over 100 supernovae, more than any individual before him, simply by photographing the same patches of sky again and again and looking for new points of light. He compiled a vast catalogue of galaxies and clusters, volume after volume, a labour most of his colleagues found tedious and he found essential. He believed that if you looked at enough of the universe, carefully, the anomalies would announce themselves. The Coma cluster was one of those anomalies, and it announced itself loudly. To see why it troubled him, you have to understand the simple piece of physics he brought to it, the virial theorem. The name is forbidding, the idea is not. Take any group of objects bound together by gravity and left alone long enough to settle into a steady state. A cluster of galaxies will do, but so will a swarm of bees around a hive, if bees were held by gravity. There is a fixed relationship in such a system between how fast the members move and how strongly they are bound. The deeper the gravitational pull holding them in, the faster they will be found moving, because it takes faster motion to keep from falling all the way to the center. Turn that around, and it becomes a scale. Measure how fast the members are moving, and you can read off how much gravity, and therefore how much mass, must be present to keep them bound. It is a way of weighing something enormous and untouchable from a great distance, using nothing but the speeds of its parts. In 1933, he turned his attention to the Coma cluster, a dense swarm of galaxies a little over 300 million light-years away, in the direction of the constellation Coma Berenices. A cluster like this is held together by gravity. The galaxies inside it are in motion, orbiting their common center, falling toward and swinging past one another in a slow gravitational dance that takes hundreds of millions of years to complete. And there is a clean mathematical relationship, it is called the virial theorem, that connects two things in any such system that has settled into balance. It connects how fast the members are moving to how much mass is holding them in. The logic is not complicated. Gravity is what keeps the cluster from dispersing. The faster the galaxies are flying around inside it, the harder gravity has to pull to hold onto them, and the harder gravity pulls, the more mass there has to be. So if you measure the speeds, you can work backward to the mass. You can weigh a cluster of galaxies without ever touching it, simply by clocking how fast its members move. Zwicky did exactly that. He took the velocities of the Coma galaxies, measured from the shifting of their light, and he made a careful, even conservative, estimate of how much visible matter the cluster contained, counting up the galaxies, assigning each a reasonable mass based on its brightness. Then he asked the obvious question, given all that visible mass, how fast should these galaxies be moving? The answer the visible matter gave him was a gentle drift. The galaxies, held by the gravity of the stars he could see, ought to be moving at a few tens of kilometers per second relative to the center of the cluster, a slow, sedate circulation. Then he looked at how fast they were actually moving. They were not drifting, They were tearing around at something closer to 1,000 kilometers per second, not a little faster than predicted, tens of times faster. The galaxies in the Coma cluster were moving with such violence that the gravity of all the visible matter in the cluster could not possibly have held them. At those speeds, the cluster should have flung its members out into intergalactic space and ceased to exist long ago. It should not have been a cluster at all. It should have been a memory. It helps to feel the scale of the mismatch, because it was not subtle. 1,000 kilometers per second is a speed that would carry you from one side of the Earth to the other in the time it takes to read this sentence. The galaxies of the Coma cluster, each one a vast wheel of 100 billion stars, were hurtling through their swarm at that pace and faster, and the cluster was holding them anyway, as it had held them for billions of years. To bind objects moving that fast, you need a gravitational grip of overwhelming strength, and gravitational grip comes only from mass. Zwicky added up all the light, converted it into a reasonable amount of matter, and found that he was short, not by 10%, not by half, but by a factor of something like 100. The luminous matter could account for roughly 1% of the grip the cluster needed. The other 99% had to be coming from something that gave off no light at all. Faced with a number that large, most people assume they have made a mistake. Zwicky checked and concluded he had not, but there it was, plainly bound, plainly intact, plainly held together by something, and the only thing that could hold it was mass, far more mass than anyone could see. By Zwicky's reckoning, the Coma cluster had to contain something like 100 times more matter than its glowing galaxies accounted for. The light was the smallest part of it, the rest was dark. He wrote it down without flinching. If this were confirmed, he said, the surprising result would follow that dark matter exists in the universe in much greater quantity than luminous matter. He used the German phrase "Dunkel Materie dark matter," and with that, almost in passing, in the middle of a technical paper, the thing got its name. He did not know what it was. He was careful to say so. It might be cold, faint stars too dim to register. It might be cold gas. It might be something stranger. The name was not a claim about composition. It was a label for an absence, for the gap between the mass the cluster needed and the mass anyone could find. The reaction from the rest of astronomy was, for the most part, to look away. There were reasons that were not merely about Zwicky's personality, though his personality did not help. The measurements were genuinely uncertain. The distance to the Coma cluster was not well known, and the distance fed directly into the mass estimate. Zwicky himself, working from the cosmological figures of his day, had some of his numbers off the assumed expansion rate of the universe was wrong at the time, which threw off the scale of everything. It was easier, and more comfortable, to assume that the discrepancy was an artifact of bad data than to accept that the overwhelming majority of the cluster's mass was made of something no telescope had ever recorded. But the easier answer did not hold up. In 1937, Zwicky came back to the problem with a longer, more careful paper. He sharpened the method. He extended it to other clusters. And even after correcting his assumptions, the discrepancy did not shrink into nothing. It stayed enormous. There was still far too much motion in these clusters for the visible matter to explain. The missing mass was not a rounding error. It was most of everything. In that same paper, Zwicky did something that, in hindsight, was extraordinary. He proposed a way to test his own claim, a way to weigh these clusters by a completely independent method that did not depend on the motions of galaxies at all. Einstein's theory of gravity, by then about 20 years old, said that mass bends the path of light. A massive enough object lying between us and some more distant source should act like a lens, warping and magnifying the light of whatever lay behind it. Zwicky argued that a cluster of galaxies, with all its hidden mass, should be massive enough to do this, to bend the light of galaxies far beyond it into distorted, brightened images. If you could find such a thing, and measure the bending, you could weigh the cluster a second way, and check whether the dark mass was really there. It was a brilliant idea, and it was about 40 years ahead of the instruments needed to carry it out. No telescope of the 1930s could have seen the effect, so the prediction was filed away, along with the problem itself, and the whole question of the missing mass went quiet. There is a temptation, looking back, to make villains of the astronomers who shrugged Zwicky off, and that would be too easy. Science is not supposed to overturn its whole picture of the universe on the strength of one difficult man's one strange measurement, however bold. Extraordinary claims do need to wait for the evidence to become overwhelming, and in the 1930s it simply was not yet. There was one cluster, measured once, by someone whose distances might be wrong and whose manner invited doubt. A careful field was right to be cautious. The failure, if there was one, was not in the caution. It was in the forgetting in letting a genuinely unsolved problem slide out of view for decades because it was uncomfortable and no one had a tool to attack it. The missing mass did not go away during those years. It simply stopped being looked at. For roughly the next 4 decades, it stayed quiet. Astronomers knew, in a back-of-the-mind way, that the clusters did not weigh what they should. It was a known oddity, a loose thread, the kind of thing you mention in a footnote and move past. It was not a crisis, because nobody had to confront it. The galaxies in a cluster are far away and faint, their motions hard to measure, and it was always possible to hope that better data would make the embarrassment disappear. What finally made the problem impossible to ignore was not a cluster at all. It was a single nearby galaxy, watched patiently, edge to edge, by an astronomer who had been told more than once that the field had no place for her, and who kept measuring anyway until the numbers left no room to look away. Her name was Vera Rubin, and she had wanted to study the stars since she was a child, lying awake watching them turn past her bedroom window in Washington. The wanting was never the problem. The doors were the problem. When she finished her undergraduate degree and tried to go on to graduate study in astronomy at Princeton, she was told not to bother applying, because Princeton did not admit women to its astronomy program. It would not admit one for another quarter of a century, so she went elsewhere. She took a master's degree at Cornell, where she sat in on lectures by some of the great physicists of the age, and then a doctorate at Georgetown, working partly at night, with a young family at home, driving herself to the university while her husband waited in the car because she did not yet drive. Her early work, a thesis, suggesting that galaxies were not scattered at random but clumped together in great groupings, was decades ahead of its time, and largely ignored, which she was getting used to. She built a career eventually at the Carnegie Institution in Washington, in its Department of Terrestrial Magnetism, and there she made a deliberate decision. She would work on problems so unglamorous, so far from the crowded and competitive frontiers of astronomy, that no one would fight her for them, and no one would scoop her. She wanted, she said, to study things she could examine quietly, at her own pace, without the elbowing. She chose to measure with great care how galaxies rotate. This was a deliberate retreat, and she made it for a reason. Earlier in her career, she had twice waded into contested, high-profile questions, and twice been savaged for it. As a young master's student, she had stood up at a meeting of astronomers and suggested, on the basis of the motions she had gathered, that galaxies might be streaming through space in bulk, not merely drifting at random, and the room had been cold, dismissive, faintly embarrassed for her. Years later, she and a colleague proposed something similar on a larger scale, a great collective flow of galaxies, and the resulting controversy was bruising enough that she resolved never again to spend her energy defending a battlefield claim. Rotation curves were not a battlefield. They were, she thought, a quiet corner where she could simply do careful work and let it stand. That the quiet corner would turn out to hold the largest mystery in the universe was not something she planned. It was something she walked into because it was the safe ground she had chosen precisely so that she could be left alone. A spiral galaxy turns. It is not rigid, like a record on a turntable, where the outer edge and the inner groove sweep around together. It is a swarm of billions of stars and clouds of gas, each one on its own orbit around the galaxy's center, each one moving at whatever speed gravity demands at its particular distance. And gravity makes a clear prediction about that. In the solar system, the planets close to the sun move fast, and the planets far out move slowly. Mercury races. Neptune crawls. The reason is that almost all the mass the sun sits in the middle, and the farther out you go, the weaker its grip, and the more leisurely the orbit. The speeds fall off with distance in a smooth, well-understood curve. A galaxy's visible matter is concentrated toward its bright central bulge, thinning out toward the dim edges. So a galaxy ought to behave, more or less, like a scaled-up solar system. The stars near the center should orbit quickly. The stars out at the faint rim far from most of the mass, should orbit slowly. Plot the orbital speed against distance from the center, and the line should rise, then bend over, then sag downward toward the edge. That falling curve was in every textbook. It was what gravity required. It was what everyone expected to see. To see it, Rubin worked with an instrument builder named Kent Ford, who had constructed an extraordinarily sensitive spectrograph, a device that could take the faint light from a small patch of a galaxy and spread it into its colors, and from the precise shift of certain bright lines in that light, read off how fast that patch was moving toward us or away from us. With Ford's spectrograph, the two of them could measure the speed of the gas at point after point across the face of a galaxy, working outward from the center toward the edge. The instrument mattered as much as the idea, and it is part of why the discovery came when it did. Ford's spectrograph used a then new kind of light-amplifying tube, a device that could take the faint glow from a galaxy's outskirts light so dim that earlier instruments would have needed whole nights to gather enough of it and intensify it enough to be recorded in a fraction of the time. Suddenly, the dim outer regions of a galaxy, the very places where the rotation curve was supposed to bend down and where no one had been able to measure speeds reliably before, came within reach. Rubin and Ford could now push their measurements out past the bright disk into the faint halo of gas beyond, exactly the territory where the surprise was waiting. A great many discoveries in astronomy are really the story of a new instrument letting someone look where no one could look before. The flat rotation curve had presumably been there in every spiral galaxy since the beginning of time. It took a particular sensitive tube in the hands of two patient people to finally see it. They began with the nearest large spiral, Andromeda, the great galaxy you can still just see with the naked eye on a dark night, a smudge of light whose photons left it more than 2 million years ago. They aimed at the bright center and measured the speed. Then they stepped outward and measured again, and again, and again, working their way toward the dim outer reaches, expecting, at every step, to watch the speeds begin their long predicted decline. The decline never came. Picture her there, because the moment is worth inhabiting. It is night, on a mountain, in a cold dome, and she is reading numbers off the spectrograph 1 point at a time, working outward from the center of Andromeda toward its edge. The first numbers behave. The speed climbs as the orbits move out from the center, exactly as it should. Then she reaches the place where the curve is supposed to turn over and start its long fall. The place every textbook promised, and the number does not fall. She moves further out, to where the visible galaxy is thinning into almost nothing, and takes another reading, expecting the speed to have dropped. It has not. It is the same. She moves further still, out past where there is any real light left to measure, and the gas is still racing along at the same impossible pace. There is no drama in the room. There is just a woman at an instrument, watching a line that refuses to bend, understanding slowly that what she is looking at cannot be held up by anything she can see. The speed climbed away from the center, as it should, and then, where it was supposed to bend over and start falling, it simply did not. It leveled off and stayed level, out past the bright disk, out where the stars thinned to almost nothing, out where there was hardly any visible matter left to hold anything. The gas was still moving, just as fast as it had been further in. The curve did not sag. It ran flat, straight out, as far as they could measure. This was not a small deviation. A flat rotation curve is a galaxy in open defiance of everything its visible mass should permit. Out at the edge, moving that fast, those outer regions had every right to fly off into intergalactic space. There was nowhere near enough visible matter to hold them on their orbits, and yet they held. Something was gripping them, something with a great deal of mass reaching far out beyond the glowing disk, far beyond where the light ended invisible but unmistakably there in its pull. One galaxy could be an oddity, so they kept going. They turned the spectrograph on the Triangulum galaxy, the third great spiral of our local neighborhood. The same flat curve. They worked through spiral after spiral, dozens of them, large and small, near and far. The result did not waver. Practically every spiral galaxy they examined did the same impossible thing. The flat rotation curve was not a quirk of Andromeda. It was a law. It was how galaxies are. Everywhere we look. Each of these galaxies, then, had to be embedded in a far larger reservoir of unseen mass. A halo of something, extending well past the visible stars, supplying exactly the extra gravity needed to keep the fast-moving outskirts from escaping. The visible galaxy, the part on every photograph, was just the bright nucleus of a much larger dark object. What is striking, looking back, is how little Rubin claimed. She did not stand up and announce that she had discovered the dark matter Zwicky had named 40 years before. She was cautious, almost to a fault. She presented the rotation curves and let them speak. The data showed, she said, that the mass of a galaxy keeps growing as you move outward. Long after the light has faded, that there is far more matter than meets the eye. What that extra matter was, she would not say. She thought it was honest to report the measurement and to resist the temptation to dress it in a theory. The facts were solid. The interpretation could wait. But the facts were enough. Coming from clusters, Zwicky's missing mass had been easy to wave away as the product of shaky measurements far out in the universe. Coming from the well-measured rotation of nearby, ordinary galaxies anyone could check, it was no longer dismissible. Rubin and Ford had not found the missing mass in some exotic, distant, special case. They had found it in essentially every spiral galaxy in the sky, including our own. The thing was not rare, it was the rule. There is a quiet justice to the fact that Vera Rubin's name is now the one most people attach to dark matter, more than Zwicky's. She spent decades being underestimated and excluded, and she answered it not with confrontation but with measurement so careful and so often repeated that they could not be argued with. She mentored generations of young astronomers, especially women, and pushed, stubbornly and successfully, to open the telescopes that had once been closed to her. There is a story she liked to tell about Palomar, the great observatory that had not, until she arrived, admitted a woman to observe, and where, accordingly, there was no women's restroom on the dome. Rather than make a speech about it, she is said to have cut a small paper skirt and taped it onto the figure on the men's room door, quietly making it a women's room too, and gone back to work. She opened doors the way she did everything, by simply walking through them and leaving them open behind her. She never won the Nobel Prize, an omission many of her colleagues considered a genuine failure of the prize rather than of her work. When she died, she had changed what we believe the universe is mostly made of, on the strength of watching galaxies spin and refusing to ignore what she saw. The great new observatory now rising in Chile to map the changing sky, the one that will photograph more of the universe than any instrument before it, carries her name. By the early 1980s, then, the case was overwhelming on two fronts at once. Whole clusters weighed far more than their light. Individual galaxies spun as though wrapped in invisible mass. The missing matter was real, and it was everywhere. But everywhere is not the same as caught. The evidence so far was the evidence of motion of things moving as though gravity were stronger than the visible mass could explain. It was indirect. It was a shadow inferred from the way the light behaved, never the dark matter itself. And a determined skeptic could still ask the hardest question. What if the motions are not lying? What if instead our law of gravity is simply wrong on these enormous scales, so that there is no missing matter at all, only a missing piece of physics? To answer that, astronomers needed to do more than weigh galaxies by their motion. They needed to see the dark mass laid out across the sky on its own terms to map it directly. And the method that finally let them do it was the very one Fritz Zwicky had written down, and the world had filed away 40 years before. The method begins with the strangest consequence of Einstein's theory of gravity, which is that gravity is not really a force in the old sense at all. In Newton's picture, mass reaches out across empty space and pulls on other mass. In Einstein's, there is no reaching, there is geometry. Mass and energy bend the shape of space and time around them, the way a heavy weight dimples a stretched sheet, and everything else simply follows the contours of that bent geometry. A planet orbiting the sun is not being tugged on a leash. It is rolling along the straightest path available to it through space that the sun has curved. Gravity, in this view, is the shape of things, and light follows that shape too. A ray of light has no mass, but it still has to travel through space, and if space is curved, the ray bends with it. Pass a beam of light close to a massive body, and its path will deflect, just slightly, drawn off course by the dent that mass has made in the geometry around it. Einstein worked this out and put a number on it. He predicted that starlight grazing the edge of the sun should be bent by a tiny, specific angle, and that you could catch it during a total eclipse, when the moon blots out the sun's glare and lets you photograph the stars that appear right beside its hidden disk. If those stars were shifted from their true positions by exactly the amount he calculated, the theory would stand. In 1919, an expedition led by the British astronomer Arthur Eddington sailed to the island of Principe, off the coast of West Africa, to photograph an eclipse and test the prediction. The stars beside the darkened sun were displaced by very nearly the angle Einstein had named. The bending of light was real. Einstein woke up, more or less overnight, to find himself the most famous scientist alive. The expedition itself was a small drama. The world had just emerged from a catastrophic war, and here was a British scientist setting out to confirm the theory of a German-speaking physicist in a gesture that struck many at the time as a quiet act of reconciliation through science. The weather very nearly ruined everything. On the morning of the eclipse, the sky over the island was clouded and rainy, and for most of the precious minutes when the moon covered the sun, there was nothing to photograph. The clouds parted only near the end, just long enough to capture a handful of usable plates showing the stars around the blacked-out sun. From that handful, measured painstakingly back in England, came the displacement that matched Einstein's prediction, and not Newton's. It is a humbling thought that one of the foundational confirmations of modern physics, and the very principle that now lets us weigh the invisible mass of the universe, came down to a brief gap in the clouds over a small island and a few faint smudges on photographic glass. What Einstein had demonstrated for a single star in the sun, Zwicky had the audacity to imagine on the scale of whole galaxies. If an object as modest as the sun could measurably bend starlight, then a cluster of galaxies, with its mountain of visible and invisible mass, should bend light far more dramatically. It should take the light of some galaxy lying far behind it and warp that light as it passed, smearing the background galaxy into arcs, multiplying it into several images, brightening it like a lens. And crucially, the amount of bending would depend on the total mass doing the bending. All of it, the dark along with the bright. Gravitational lensing would weigh the dark matter directly by the only thing it reliably does: it bends the path of anything that comes near, including light. There is an irony worth pausing on. Einstein himself had considered the idea of one star lensing another, worked out the mathematics, and concluded, in a short paper, that there was no real hope of ever observing it. The alignments required would be too precise, the effect too small, the chance too remote. He published the calculation almost apologetically, at the urging of an amateur who had pestered him about it, and called the whole thing of little practical value. He was thinking of stars, where he was right. What he did not pursue, and what Zwicky saw the very next year, was that you did not need stars. You needed something far more massive, a whole galaxy, a whole cluster of galaxies, and then the effect was not vanishingly rare but inevitable, common, waiting to be found the moment our instruments could resolve it. The most famous physicist of the age looked straight at gravitational lensing and saw a curiosity. The difficult man at Caltech looked at it and saw a way to weigh the invisible. For 40 years the idea sat unused because no instrument could see the effect. Then, in 1979, 3 astronomers, Dennis Walsh, Robert Carswell, and Ray Wayman, were studying a distant quasar, one of those blindingly bright cores of young galaxies, and found something that should not have been there. 2 quasars, side by side, almost impossibly alike. Same colour, same spectrum, same redshift, as if one had been copied and pasted next to the other. It was not 2 quasars. It was one quasar, lying far in the background, whose light had been split into 2 images by the gravity of a galaxy sitting between it and the Earth. The intervening galaxy had bent the light around both sides of itself, and we were seeing the same object twice. It was the first gravitational lens ever recognized, and Zwicky's 40-year-old prediction had finally come true. Since then, lensing has grown into one of the most powerful tools astronomy possesses, and it comes in 2 strengths. When the alignment between us, the lens, and the background object is nearly perfect, the effect is dramatic. The background galaxy is stretched into long, bright arcs, drawn out into smears that curve around the lensing mass. In the rare cases where the alignment is almost exact, The background light is wrapped all the way around into a complete circle, an Einstein ring, a luminous halo encircling the dark mass that made it. This is strong lensing, and it is beautiful, and it is uncommon, because it needs that knife-edge alignment. These rings and arcs are among the most striking images astronomy has ever produced, and they are not merely pretty. Each one is a measurement. The exact shape of an Einstein ring, how complete it is, how thick, how it bulges or thins around its circumference is set by the precise distribution of mass in the foreground galaxy doing the lensing. So, from the geometry of the ring, astronomers can weigh that galaxy and map how its mass is spread out, including the part that gives off no light. Time and again. When they do this, they find the same thing the rotation curves found. There is far more mass than the visible starlight can account for, and it extends far beyond the glowing parts of the galaxy. A galaxy photographed as a bright, compact smudge turns out, when weighed by the ring of light, it bends around itself to be the small visible core of something much larger and dark. The lensing and the rotation curves, two completely independent methods, hand back the same verdict from different directions, which is exactly the kind of agreement that turns a suspicion into a fact. Far more common, and in many ways more useful, is weak lensing. Most of the time the alignment is not special at all, and the bending is gentle. A background galaxy is not split or ringed, only slightly stretched, its apparent shape squeezed by a fraction of a percent. You could never spot that in a single galaxy. You have no way of knowing what shape it was supposed to be. But if you photograph millions of distant galaxies across a wide patch of sky, and you measure all their shapes, a pattern emerges from the crowd. The faint distortions are not random. They align subtly, swirling around the places where mass is concentrated in the foreground. From that statistical shimmer in the shapes of millions of galaxies, you can reconstruct where the mass lies, including the mass you cannot see. This is how we now make maps of dark matter. Great surveys with names like the Kilo Degree Survey and the Dark Energy Survey have spent years photographing huge stretches of the sky, measuring the shapes of hundreds of millions of galaxies and turning those measurements into maps of the invisible. And in 2023, a spacecraft built specifically for this work, named Euclid, went into orbit with a mandate to chart the dark matter across a third of the entire sky, in sharper detail than anything before it. By reading the faint lensing in the shapes of billions of galaxies, the maps that come back are remarkable in what they show. The dark matter is not a smooth fog filling space evenly. It is structured. It hangs in a vast web-dense knots, where the great clusters of galaxies sit, long thin filaments of dark mass running between the knots, and huge near-empty voids in between, like the spaces inside a sponge or the bubbles in a head of foam. And the bright matter, the gas and the galaxies, follows this dark web faithfully. The luminous universe is strung along the filaments like dew along a spider's thread. The web came first, the visible cosmos condensed onto it. We are looking at the skeleton of everything, finally made visible not by light it emits, because it emits none, but by the way it bends the light of things behind it. The scale of these maps is hard to take in. A single one of them can cover a patch of sky and a depth of space holding tens of millions of galaxies, each galaxy a city of 100 billion stars, all of them reduced, in the map, to faint traces of where the dark mass lies. And when you compare these observed maps to what a universe made of cold, slow, dark matter ought to produce when you run the physics forward in an enormous computer simulation, starting from those faint early ripples and letting gravity sculpt the dark matter over billions of years, the simulated web and the real web look like siblings. The same filaments, the same knots, the same voids, the same overall texture of a cosmos spun into threads. That agreement is one of the quieter triumphs of the whole picture. We can take the dark matter we cannot identify, assume only that it is cold and gravitates, simulate the growth of the universe from its first ripples, and reproduce the actual large-scale structure of the sky. Whatever the dark matter is, it behaves, on the grand scale, exactly as though it is real, simple, and everywhere. So lensing answered Rubin's quiet caution and the skeptic's hard question, at least partway. The dark matter was not just an inference from spinning galaxies. Here it was, mapped across the sky, weighed by the bending of light, laid out in filaments and halos. It was real, and it was the dominant structure of the universe. But mapping is not the same as identifying. A lensing map tells you where the mass is and how much of it there is. It tells you nothing about what the mass is made of. Light reveals an ordinary substance by the colours it emits, and absorbs every element has its own signature, its own pattern of bright and dark lines, a fingerprint written into the spectrum. Dark matter has no such fingerprint because it does not touch light at all. It casts no spectral lines. It has no colour, no glow, no shadow in the ordinary sense. It announces itself only through gravity, and gravity tells you a thing's weight and nothing about its nature. Still, the skeptic's hardest question had not been fully closed. Maybe the argument still ran. There is no dark substance at all. Maybe gravity itself simply works differently across these vast distances, and what looks like missing mass is really a flaw in our law of gravity. Lensing maps, on their own, could not entirely rule that out, because a modified gravity might bend light in unexpected ways too. To settle it, the universe would have to perform a particular experiment, one where the dark matter, if it existed as real stuff, would be physically torn away from the ordinary matter and left somewhere it visibly did not belong. We could not arrange such an experiment. It would take a collision between worlds. As it happens, the universe had already run it for us, more than 100 million years ago, and the light from it was only now arriving. The experiment is called the bullet cluster, and it is the closest thing this whole story has to a smoking gun. It is not one cluster but two, caught in the act of passing through each other. A smaller cluster of galaxies has driven straight through a larger one, like a bullet through a target, which is where the name comes from. The collision happened roughly 150 million years ago. As we see it, the light has been crossing the gulf to us ever since, and it happened at a staggering speed, the two clusters slamming together at thousands of kilometers per second. On the scale of galaxies, this is one of the most violent events the universe knows how to stage. To understand why this particular crash matters so much, you have to know that a cluster of galaxies is made of three quite different things, and they behave very differently in a collision. There are the galaxies themselves, but the galaxies, for all their brightness, are almost the least of it by mass. There is the hot gas, an immense diffuse cloud of it filling the space between the galaxies, so hot it glows in X-rays, and this gas actually outweighs all the stars in all the galaxies put together. And then there is the dark matter, which outweighs even the gas, several times over. Stars, gas, dark matter, that is the cluster, in increasing order of mass and decreasing order of visibility. Now send two such clusters through each other, and watch what happens to each component. The galaxies, despite their size, are mostly empty space. The distances between stars are so vast that when two clusters of galaxies interpenetrate, the individual galaxies almost never actually hit anything. They sail straight through the oncoming cluster like two swarms of gnats passing through one another, barely grazing, and come out the far side still moving, hardly slowed at all. The hot gas does not get off so lightly. Gas is continuous. It cannot pass through other gas without consequence. When the two great clouds of gas met, they collided in the fullest sense. They rammed into each other, heated, shocked, and dragged to a halt. The gas of each cluster piled up in the middle, slowed by the gas of the other, like two streams of water hitting head-on. So the gas, which is most of the ordinary matter, got stripped out of the galaxies it had been travelling with and left stranded in the centre, between the two clusters, while the galaxies themselves coasted on past it and out the other side. That separation is the gift. After the collision, the ordinary matter of these clusters is in two different places. The galaxies are out front, on either side, having sailed through. The gas most of the normal mass is stuck in the middle, glowing in X-rays. Ordinary matter has been physically pulled apart from itself. So now ask the decisive question: where is the gravity? Where is the bulk of the mass? You can answer it independently, without assuming anything about dark matter, by mapping the cluster's gravity through weak lensing, by measuring how the whole system bends the light of the galaxies far behind it. If there were no dark matter, and the missing mass were really just a misunderstanding of gravity, then the gravity should track the ordinary matter, and most of the ordinary matter is the gas. Sitting in the middle, the lensing should peak where the gas is. That is not what the map shows. The map shows the gravity concentrated in two clumps out on the flanks, with the galaxies. The great bulk of the mass had sailed straight through the collision, along with the galaxies, untouched, leaving the gas behind. The mass and the gas are in different places. Most of the matter in the bullet cluster is not where most of the ordinary matter is. This is exactly, precisely, what dark matter is supposed to do, and very hard to explain any other way. Dark matter does not feel the ramming and shocking that stop the gas, because dark matter does not interact with ordinary matter except through gravity and barely with itself. So when the clusters collided, the dark matter, like the galaxies, simply passed through, indifferent to the wreck of gas it was leaving in the middle. It went out the far side because almost nothing could touch it. The gas got stuck because gas gets stuck. And the gravity followed the dark matter out on the flanks, exactly where a real, collisionless, invisible substance would have ended up. A modification of gravity has a very hard time producing this. In a pure modified gravity picture, with no dark substance at all, the extra gravity has nowhere to come from except the visible matter, and the visible matter, by mass, is mostly that central gas. The gravity ought to sit where the gas sits. Instead, it sits a long way off, out where the nearly massless starlight is and the gas is not. To make modified gravity reproduce the bullet cluster, you have to bolt on so many extra assumptions that the elegance, which was its whole appeal, quietly drains away. The result, published in 2006, did not silence every alternative theory overnight, but it changed the center of gravity of the entire debate. After the bullet cluster, the burden of proof shifted. Dark matter was no longer the exotic claim that needed defending. It had become the natural reading of the evidence, and it was the alternatives that now had the harder case to make. The picture itself, when astronomers assembled it, was almost theatrical in how clean it was. The glowing gas, mapped by an orbiting X-ray telescope, showed up as a bright wedge driven back into the center of the collision, even shaped a little like a bullet, with a shock wave curling off its front edge from the violence of the impact. The mass, mapped entirely separately by the gentle distortion of background galaxies, showed up as two faint clumps sitting well apart from that wedge, out where the galaxies were. Two different instruments, measuring two different things, the heat of the gas and the bending of distant light. And they disagreed about where the cluster's substance was, in exactly the way they should if most of that substance were dark, collisionless, and long gone past the wreck. You could lay one image over the other and simply see the dark matter and the ordinary matter occupying different ground. Honesty requires admitting that not every colliding cluster has told quite so tidy a story. There is another famous wreck, sometimes nicknamed the train wreck for how confused it looks, where early maps seem to show a clump of mass sitting right where the gas was, with no galaxies to go with it, apparently the opposite of what the bullet cluster shows, and a genuine headache for the simple picture. Later, deeper observations have softened that puzzle, and the balance of the evidence still rests heavily on the bullet cluster's side, but the episode is a useful reminder. These are not laboratory experiments run under controlled conditions. They are enormous, messy, once-only collisions seen from a single angle across vast distances, and the universe does not always hand us a clean result. The strength of the dark matter case is not that every single cluster cooperates. It is that so many independent lines of evidence, the clean ones and the messy ones together, keep pointing the same way. And the bullet cluster has not stood still since. It has been observed again and again, with steadily better instruments. Other colliding clusters have been found showing the same separation, the mass parting company with the gas, the dark matter sailing on. In recent years, the James Webb Space Telescope has turned its enormous mirror on the bullet cluster and produced the sharpest map yet of how the mass is laid out, stitched together from the lensing of many background systems at once. The new maps trace the dark matter in finer detail than ever, and they also let astronomers ask a subtler question, not just where the dark matter is, but whether it feels itself. If dark matter particles bumped into one another even slightly as they passed through the collision, the dark clumps would have been smeared or slowed, just a little. The sharper the map, the tighter the limit you can put on that self-jostling, and the limit is very tight. The dark matter appears to pass through itself almost as cleanly as it passes through everything else, a substance so aloof it barely interacts even with its own kind. So this is where the gravitational case comes to rest, and it is a strong place to rest. The rotation of galaxies, the motion of clusters, the bending of light into maps of the invisible web, and the clean separation of mass from gas in the bullet cluster all point, from completely different directions, at the same conclusion. There is far more matter in the universe than we can see. It behaves like a real, cold, collisionless substance, and it is the dominant gravitating stuff in the cosmos. Every one of those arguments is about what dark matter does. None of them touches what it is. And before we go hunting for what it is, before we descend into the mines where physicists have spent 40 years waiting for it to reveal itself, it is worth pausing on what this invisible substance has already done, because it did not merely tug on some galaxies, it built the place. Long before there were galaxies to spin or clusters to collide, the dark matter went first and laid down the structure that everything else, including you, would later be built upon. Lie still for a moment with the strangeness of the bullet cluster, because it is the closest we have come to seeing the dark matter caught in the open. Two worlds of galaxies collided more than 100 million years ago, and the wreckage sorted itself, by the simple logic of what touches what, into the part that could be stopped and the part that could not. The gas piled up, glowing, in the middle. The dark matter sailed on through, untouched, indifferent, carrying most of the mass with it to the far side. And we can see both, mapped by different instruments, sitting in different places, the visible separated from the heavy, the substance of the universe pulled apart from its light. It is as direct a portrait of the dark matter as anything we possess, and it is still only a silhouette. We can see where it went. We can see how much of it there was. We can see that it ignored everything in its path, including itself, and we still cannot say what a single grain of it is. To see what the dark matter did, go back to the beginning to the universe, as it was a few 100,000 years after the Big Bang, before there was a single star anywhere. It was hot, and it was dense, and it was very nearly smooth, almost the same everywhere, but not perfectly. There were faint ripples in it, regions very slightly denser than average, and regions very slightly thinner, laid down in the first instance of the universe's existence and stretched to enormous size as the cosmos expanded. We are not guessing at this. We can see those ripples directly, frozen into the oldest light in the sky, the cosmic microwave background, the afterglow of the hot early universe, which carries an image of how lumpy the cosmos was when it was less than 1 million years old. The lumpiness was tiny. The difference between the densest spots and the thinnest was about 1 part in 100,000, a whisper of unevenness on an almost perfectly smooth sea. Hold that picture for a moment, lying there in the dark, because everything you are and everything you have ever seen grew out of those faint ripples. There were no stars yet, no galaxies, no planets, no atoms even, in the form we know them, just a vast, glowing, near-uniform warmth, expanding and cooling, marked only by the faintest unevenness, the slight excess of matter here, the slight lack of it there, and one of those very slightly denser patches, billions of years and a long chain of consequences later, became the gas cloud, that became the galaxy, that became the star, that became the dust, that became the sun and the earth and the carbon in your hands. You can trace a clean line in principle, from one faint ripple in that early warmth to the body lying in this room. The seed of you was a whisper of unevenness in a sea of light, and the thing that took that whisper and grew it into a galaxy, the thing that did the work, was the dark matter. That whisper was the seed of everything. Gravity takes any region that is slightly denser than its surroundings and makes it denser still, because the extra mass pulls in more matter, which adds more mass, which pulls in more. Left alone, the faint ripples would have grown, slowly, into the first structures. But there is a complication, and the complication is the whole reason dark matter matters here. Ordinary matter, in that early hot era, was not free to fall together. It was locked in a furious embrace with light. The universe was so hot that atoms could not yet hold together. Matter was a charged plasma of bare nuclei and loose electrons, and charged particles and light are inseparable. The light scattered off the particles constantly, ceaselessly, like a fog, so thick you could not see your own hand. And that constant battering of light held the ordinary matter up. Every time gravity tried to pull the plasma together into a denser clump, the pressure of all that trapped radiation pushed it back apart. Ordinary matter could not collapse. It could only slosh, trapped, unable to build anything. Dark matter felt none of this. It does not touch light. The fog that held ordinary matter prisoner was, to dark matter, not there at all. So while the ordinary matter was stuck sloshing in the glare, the dark matter was free to do the one thing it does fall together, under its own gravity, quietly, unopposed, and it did. Through that whole early era, the dark matter was already collapsing into the denser spots, deepening them, building wells of gravity throughout the young universe in visible pits, scattered everywhere, growing steadily deeper while the ordinary matter could only wait. Then, a few 100,000 years in, the universe cooled enough that the plasma finally settled into neutral atoms. The electrons and nuclei joined, the fog lifted, the light streamed free, and that release of light is the very glow we now see as the cosmic microwave background. With the fog gone, the ordinary matter was suddenly let off its leash. The radiation pressure that had held it up for so long vanished, and at last it could fall. But it did not fall into a smooth, featureless expanse. It fell into a landscape that the dark matter had already sculpted. All those deep invisible wells were waiting, and the ordinary gas, freed at last, came pouring down into them. The dark matter had dug the channels. The ordinary matter ran along them and pooled at the bottoms. Inside the deepest wells, the gas grew dense enough to heat, to compress, to ignite, and the first stars caught fire, somewhere between 100 and 200 million years after the beginning, in the hearts of dark matter halos that had been preparing the ground for them all along. Think of it as the difference between rain falling on level ground and rain falling on a landscape already carved with valleys. On level ground, the water spreads thin and goes nowhere. It takes an age for any pool to gather, but let the valleys be cut first, deep and waiting, and the same rain runs straight down their sides and collects in the low places, gathering fast into rivers and lakes. The dark matter cut the valleys while the ordinary matter was still held up in the glare, so when the rain of gas was finally released, it did not have to wait and spread and slowly find its own way together. The low places were already there. The gas knew exactly where to go. That head start, those pre-dug wells, is the whole reason the universe was able to build galaxies as quickly as it did, in the time it has had. Without the dark matter to carve the landscape in advance, the rain would still be spreading thin across a level plain, and the cosmos would be dark. This is the sense in which the dark matter went first, and it is not a metaphor. It is a sequence of cause and effect. The dark matter collapsed early because nothing held it back. Its gravity carved out the structure. The ordinary matter, when it was finally released, fell into structure that was already there and built the visible universe inside it. The stars, the galaxies, the great web. Reverse the order and ask what would have happened with no dark matter at all, and the answer is sobering. Ordinary matter alone, starting from those faint 1 part in 100,000 ripples, would not have had time to assemble itself into galaxies in the age the universe has so far reached. The structures we see could not have formed. The cosmos would be a thin, dark, formless drift of gas, and nothing in it would ever have lit. There is one more thing the structure tells us, and it is a genuine clue to the dark matter's nature, almost the only direct clue we have. The dark matter had to be slow. When physicists say the dark matter is cold, that is what they mean, that the particles in the early universe were moving sluggishly, not whipping around near the speed of light. The distinction matters enormously for how structure grows. If the dark matter had been hot, fast-moving, light, racing through the young cosmos, it would have streamed straight out of the small, dense ripples before they could deepen, smearing out all the fine structure and leaving only the largest lumps to form first. The universe would have built its biggest structures earliest and broken them into galaxies later, from the top down, but that is not what we see. We see the opposite. We see small things forming first, the first stars, the first small galaxies, and merging, over billions of years, into the large structures from the bottom up. The universe assembled itself small to large, and only cold, slow dark matter produces that. So whatever the dark matter is, this is one solid fact about it. Its particles were moving slowly when it mattered, which means, most likely, that they are individually rather heavy, or were born cold. It is a faint description of a stranger we still cannot see, but it is a real one, written into the order in which the cosmos was built. This also quietly rules out a candidate that once seemed natural, We already know of a particle that is abundant, nearly invisible, and barely interacts the neutrino. For a while it was tempting to think neutrinos might be the dark matter, but neutrinos are fast. They are the very definition of hot. A universe whose dark matter was neutrinos would have grown its structure top-down and would look nothing like the one we live in. The known neutrinos cannot be the answer. The dark matter has to be something colder, and so far, something we have never met. There is one more fingerprint of the dark matter pressed into the large-scale universe, and it is among the most beautiful. Back when ordinary matter was still locked in its plasma, battered by light, the pressure of that trapped radiation drove sound waves through it, real pressure waves, rippling outward through the early cosmos. The dark matter, deaf to light, did not ride those waves. It sat still in its gravitational wells while the ordinary matter rang like a struck bell. Then, when the fog lifted and the plasma settled into neutral atoms, the sound waves froze. The ordinary matter was left slightly piled up at a particular distance from each original lump, the distance the last sound wave had travelled before the music stopped. Again, that frozen ripple left a faint preferred spacing in how galaxies are distributed, a gentle excess of galaxy pairs, separated by one characteristic distance, repeated all across the sky. We can measure it. It is there, exactly where the physics says it should be a standing ruler, hundreds of millions of light years long, laid down by sound in the first moments and preserved in the arrangement of galaxies ever since. And the size of that ruler depends, again, on how much dark matter the early universe held. The same dark matter shows up in the spinning of galaxies, the bending of light, the collision of clusters, the texture of the cosmic web, and now in the faint frozen music of the early plasma. From every direction, the accounting comes out the same. So follow the chain all the way down to where you are lying. The carbon in the cells of your body was forged in the core of a star and scattered when that star died. That star formed inside a galaxy. That galaxy condensed inside a halo of dark matter. The halo was there, holding its shape, before the star, before the galaxy, before any of it. Take away the invisible scaffolding, and the whole structure never rises. You are, in a long and unbroken sequence, downstream of the dark matter. It is not exaggeration to say that you exist because, in the first 100 million years, the dark matter fell together first and made a place for everything else to form. And it never left. It is not a relic of the early universe. Its work finished. The halos are still here, still holding their galaxies. Ours is still wrapped around the Milky Way, vast and invisible, and the solar system is still sweeping through it. Let yourself sit inside that for a moment. You are not lying still. The Earth is turning and carrying you around the Sun, and the Sun is falling around the center of the galaxy at something like 230 kilometers every second, dragging the whole solar system with it. And all of that motion is happening inside the dark matter halo. From your point of view, then, there is a faint wind, not of air, of dark matter, streaming past and through the moving Earth, through the dark room, through the bed, through you, at hundreds of kilometers a second. Billions of those particles cross your body every second of your life. They have crossed you in every second you have ever lived. Not one of them has ever touched you in any way you could feel. You have spent your entire existence soaked in the stuff that makes up most of the matter in the universe, and you have never once noticed, because there is, as far as your body can tell, nothing there to notice. That is the strangeness we have to sit with. The dominant matter of the cosmos is not far away. It is the most intimate thing imaginable. It is inside you, right now, in its billions, and it asks nothing and leaves no trace. And we still do not know what a single particle of it is. That is the question that finally drove physicists off the mountaintops and out of the observatories and underground down into deep mines, into the most carefully shielded rooms ever built, to wait in the dark for one of these particles to do the one thing it almost never does, to bump, just once, into something we can measure. To catch a dark matter particle, you first have to get away from everything else. And that turns out to be the hardest part. The surface of the Earth is a noisy place, in a way that has nothing to do with sound. It is constantly being rained on by cosmic rays, high-energy particles from space, from the Sun, from exploded stars far across the galaxy that comes sleeting down through the atmosphere and through everything on the ground, including any detector you might build. Every one of those strikes looks, to a sensitive instrument, a little like the event you are hoping for. If you tried to watch for the whisper-faint touch of a dark matter particle on the surface, it would be like trying to hear a single dropped pin in the middle of a thunderstorm. The storm would drown out everything. So the experiments go down. Deep underground, the rock overhead acts as a shield, soaking up the cosmic rays before they can reach the detector. The deeper you go, the quieter it gets. These experiments are run beneath mountains and at the bottoms of mines under more than a kilometre of Italian rock in the Gran Sasso laboratory, 2 kilometres down in a Canadian nickel mine, and, for the largest of them, nearly 1.5 miles beneath South Dakota, in the tunnels of a worked-out gold mine. Down there, almost nothing penetrates. The cosmic storm is held off by the mountain. Only the most ghostly particles can still reach that far down the neutrinos that pour out of the sun, and in theory, the dark matter. It is worth pausing on what this actually costs in human effort, because the silence these experiments collect is expensive silence. To get to the largest of them, researchers ride a cage down a mine shaft that once carried gold miners, descending through nearly 1.5 miles of rock into chambers that have been scrubbed and sealed and rebuilt into some of the cleanest spaces on Earth. And the cleanliness is not ordinary cleanliness. Every component of the detector, every bolt, every wire, every litre of liquid has to be screened for the faintest natural radioactivity, because the rock of the planet, the air, even the steel of an ordinary tool, all carry a low background hum of radiation that would drown the signal they are listening for. Some of these experiments use metals smelted before a certain date in history, sought out specifically because they were forged before the first nuclear tests scattered a thin layer of new radioactivity across the entire globe. They hunt for old lead from sunken ships, for steel poured before the atomic age, because even that faint modern contamination is too loud. The whole enterprise is an act of subtraction, an attempt to remove, one source at a time, everything in the universe except the one whisper they are straining to hear. And then they wait, for years, in the deepest quiet humans have ever engineered, to find out whether the whisper comes. The largest of these detectors is an experiment called LZ, and at its heart sits something deceptively simple: a great tank of liquid xenon, a heavy, clear, inert element, chilled to around 100 degrees below zero on the Celsius scale, so that it pools as a cold, transparent liquid. There are several tons of it, held in a chamber roughly the size of a small room, and it is surrounded, layer upon layer, by shields against every stray disturbance, tanks of water, walls of other materials, and an outer system whose only job is to recognize and reject anything that comes in from outside. The xenon itself is purified to an almost unimaginable degree, scrubbed of every trace of natural radioactivity, because the faintest contamination would glow like a flare against the darkness they are trying to keep. The idea behind it is patient and clean. A dark matter particle, if it is the kind physicists long suspected, almost always passes straight through the rock, through the shields, through the xenon, untouched. But almost always is not the same as always. Every so often, very rarely, one of them should happen to pass close enough to the nucleus of a xenon atom to actually strike it a direct hit at the scale of a single atomic nucleus. When that happens, the nucleus recoils, kicked like a ball struck by something invisible, and that tiny recoil leaves 2 faint signatures behind. It makes a minute flash of light, and it knocks loose a few electrons. The detector is ringed with sensors so sensitive they can register a single particle of light, and they watch the xenon continuously, day and night, year after year, waiting for that particular double signature, a small flash and a small spark of liberated charge that would mark the moment a piece of the dark universe finally touched a piece of the visible one. The particle they were built to catch has a name. For decades, the leading suspect for dark matter was a hypothetical thing called a WIMP, a weakly interacting massive particle. The appeal of the WIMP was that it did not have to be invented from scratch just to solve this one problem. It fell, almost for free, out of an elegant idea in particle physics called supersymmetry, a proposed deep symmetry of nature that would pair every known particle with a heavier, undiscovered partner. The lightest of those partners would be stable, heavy, and barely able to interact with anything, which is to say, it would have exactly the properties dark matter seems to need. Better still, if you assumed such particles had been produced in the heat of the early universe, the leftover amount worked out, almost suspiciously well, to roughly the quantity of dark matter we actually observe. The pieces fit so neatly that for a long time the WIMP was not just a candidate, it was the front-runner, the favourite, the thing nearly everyone expected the detectors to find. That suspicious neatness even had a nickname, the WIMP miracle, and it is worth understanding why it seduced a whole generation of physicists, because the logic really is lovely. In the first instance, after the Big Bang, everything was so hot and dense that particles of every kind were constantly being created and destroyed, in balance. As the universe expanded and cooled, the heavier particles could no longer be made, and they began to annihilate away. But the universe was also thinning out, and at some point the surviving particles became so spread apart that they could no longer find each other to annihilate. Whatever was left at that moment was frozen in a permanent leftover, a relic abundance, locked into the cosmos for good. And here is the miracle. If you take a particle that interacts with the strength of the weak nuclear force, and a mass in the range the weak force naturally suggests, and you compute how much of it would freeze out, the answer comes out right. Not approximately right. Right, to roughly the amount of dark matter we measure. Two completely unrelated branches of physics, the particle physics of the weak force and the cosmic accounting of dark matter, appeared to be pointing at the same object. It looked less like a coincidence than like a clue. It told a generation of physicists exactly what to build and what to expect. So they built the detectors, each more sensitive than the last, and they waited. And the WIMP did not come. LZ has now watched its xenon for well over a year of continuous running, the largest and most sensitive search of its kind ever performed, and it has seen no sign of a WIMP. Nothing. LZ. Where earlier, cruder detectors might have missed a faint signal, this one would not have. The experiment is now more than 3 million times more sensitive than the instruments physicists were using when this hunt began decades ago. It has pushed the possible properties of a WIMP into a smaller and smaller corner, ruling out vast ranges of what such a particle could be, and in all that searched-out territory, it has found only silence. The team's spokesperson put it plainly when the latest results came out, saying that they see no direct evidence of dark matter, that the detector is performing beautifully, and that they will keep pushing it to chase the models that remain. There was no disappointment dressed up as discovery, just the honest report. We looked, harder than anyone ever has, and it was not there. There is one detail in all this that is almost too fitting to be true. The same detector that has failed to find dark matter has succeeded, for the first time, in catching something else, the neutrinos pouring out of the center of the sun. Neutrinos are themselves famously elusive, ghosts that stream through the Earth in their trillions without noticing it. To register them at all is an extraordinary achievement, and it proves beyond doubt that the detector works, that it is sensitive enough to catch even the faintest whispers nature offers. One of the analysts described the power of it well, that it is one thing to calibrate against a source you control, and quite another to point your instrument at the raw nuclear fire of the sun and find that the trickle of particles you catch matches the prediction exactly. The instrument is not broken, it is not blind. It can hear the faintest sounds in the universe. It simply does not hear the dark matter, because the dark matter is not making the sound the WIMP was supposed to make. And LZ is not alone in its silence. A comparable xenon experiment beneath the Gran Sasso Mountains in Italy has searched and found nothing. A large experiment in China, using its own tons of xenon, the same. Others, using liquid argon, using crystals of germanium and silicon chilled to a hair above absolute zero, all of them peering into the dark for the same faint touch. All of them, so far, empty. Every major direct search for the WIMP has come back with the same answer. The pattern is not a single failed experiment. It is a chorus of silence from every direction at once. There is one stubborn exception, and it is worth being fair about it. For more than 2 decades, an experiment under the same Gran Sasso Mountain, using crystals of sodium iodide rather than xenon, has reported a signal, and not just any signal, but one that rises and falls over the course of each year, exactly as you might expect if the Earth were sweeping through a stationary halo of dark matter, moving into the wind in one season and with it in another. On its face, that annual rhythm is tantalizing, just the signature dark matter should leave. But no other experiment has been able to reproduce it, and several built specifically to check it have looked in the same way and seen nothing. So it sits there, unresolved, almost certainly some subtle seasonal effect within the experiment itself, rather than a true detection, most physicists believe, but never quite explained away, a single dissenting voice in the chorus that no one has managed to either confirm or silence. There is also a strange horizon now coming into view for this whole enterprise, and the solar neutrinos are the sign of it. As the detectors grow ever more sensitive, they begin, inevitably, to catch the neutrinos streaming from the sun and from the wider cosmos, and a neutrino striking a nucleus looks almost exactly like a dark matter particle striking a nucleus. This means there is a flaw, a fog of neutrinos that the experiments are now starting to wade into, beneath which it becomes genuinely hard to tell a dark matter signal from the steady background hum of the universe's own neutrinos. The fact that LZ has now caught solar neutrinos means it has reached the edge of that fog. The search can still go deeper, with cleverer techniques, but the easy gains are ending. The detectors have nearly run out of darkness to hide in. Meanwhile, the other half of the WIMP's promise was failing too. The Large Hadron Collider, the immense particle accelerator buried in a ring outside Geneva, was supposed to be the place where supersymmetry, the elegant theory that gave us the WIMP, would finally show itself, where those heavy partner particles would be created in the violence of head-on proton collisions. The collider has now run for well over a decade at the highest energies humans have ever produced, and it has found no trace of them. The simplest, most beautiful versions of supersymmetry, the ones that predicted the WIMP most cleanly, are now squeezed almost to the point of vanishing. The theory that made the WIMP seem inevitable has not delivered, and the detectors built to catch the WIMP have caught nothing. It is worth being clear about what this silence is and is not. It is not evidence that dark matter does not exist. The gravity is still there, the galaxies still spin, the light still bends, the bullet cluster still holds its secret. The silence is something more specific and more humbling. It is evidence that dark matter is probably not the thing we were most sure it would be. For 40 years, the WIMP was the obvious answer, the safe bet, the particle the whole field leaned toward. The detectors were, in a real sense, built around that expectation, and the universe has spent those 40 years quietly refusing to confirm it. The search has not failed. It has succeeded in telling us, with enormous and hard-won precision, where the answer is not. There is a lesson buried in this that reaches beyond dark matter, and it is one of the quieter virtues of the whole enterprise. The WIMP was beautiful. The coincidence that made it seem inevitable, that lovely matching of the weak force to the cosmic abundance, was the kind of thing that feels, to a physicist, like a glimpse of how nature must be put together. And it may yet turn out to be true. The WIMP is not dead, only cornered, its remaining hiding places few and shrinking. But the experience of the last 40 years is a reminder that the universe is under no obligation to be as elegant as we find convenient. We built a generation of magnificent instruments on the strength of a beautiful idea, and the instruments worked perfectly, and the beautiful idea has so far not been confirmed. That is not a waste. It is how honest inquiry is supposed to feel. You follow your best guess all the way to the bottom of a mine. You wait there for years in the dark, and you let the silence correct you. The detectors did not find what they were looking for. They found something arguably more valuable, which is the truth that they were looking in the wrong place, and a much sharper sense of where to look next, which forces a harder question to the surface, the one that has waited politely in the background this whole time. If the most natural particle is not there, then perhaps the problem is not which particle. Perhaps there is no particle at all, and we have been wrong in a deeper way, wrong about gravity itself. That possibility deserves a fair and serious hearing, because for 40 years one physicist and his successors have argued exactly that, and they have not been cranks. They have been right about more than their critics like to admit. The fair alternative is called modified Newtonian dynamics, usually shortened to its initials MOND, and it was born from a simple, stubborn refusal to add invisible matter to the universe. It was proposed in 1983 by an Israeli physicist named Mordechai Milgrom, working at the Weizmann Institute. Milgrom looked at the same flat rotation curves that Vera Rubin had measured. galaxies whose outskirts moved far too fast for their visible mass, and he asked a different question from everyone else. The standard response was to say, there must be extra, unseen mass out there, supplying the missing gravity. Milgrom asked instead, what if there is no missing mass? And what if, out in those faint outer regions, gravity simply does not work the way Newton said it does? It took a certain nerve to ask that, and Milgrom paid for it in the usual coin, to suggest that Newton's law of gravity, one of the most successful and most tested ideas in the history of science, the law that lands spacecraft on other worlds might quietly break down in the outskirts of galaxies, was, to most physicists, close to heresy. It was far more natural, far more conservative to add a new kind of invisible matter than to touch the sacred law of gravity itself. Milgrom spent years on the idea largely alone, and for a long time the mainstream regarded his proposal as a curiosity at best. He has said, with some weariness, that he always expected to be in the minority, and that he made his peace with it. What kept the idea alive was not its popularity, but its strange, persistent success at the one thing it was built for. Whatever else you think of it, modified gravity predicted the precise way real galaxies rotate, with an accuracy that has never been comfortably explained away. A wrong idea is not usually that good at its job. His idea was precise rather than vague. Newton's law of gravity has been tested to exquisite accuracy in the solar system and on Earth, so Milgrom did not propose to overturn it where it works. He proposed that it changes only in a regime we had never been able to test before, the regime of extraordinarily gentle acceleration. In the outskirts of a galaxy, a star feels a gravitational pull so faint that it is millions of times weaker than the pull you feel standing on the ground, gentler, by a vast margin, than any gravity ever measured in a laboratory. Below a particular threshold of gentleness, somewhere around 1 part in 100 billion of the gravity that holds you to the Earth, Milgrom suggested that gravity stops weakening as fast as Newton said. It hangs on more strongly than it should, and that small stubbornness, applied to the faint outer reaches of a galaxy, would make the stars out there orbit faster than Newton allowed exactly as fast, it turned out, as Rubin had seen them move. The remarkable thing about Milgrom's proposal is how well it works in the place it was designed for. With a single new constant that one threshold of acceleration MOND reproduces the flat rotation curves of spiral galaxies with startling accuracy, not just roughly but in detail, galaxy after galaxy, matching the exact shape of the curve from the bright center to the dim edge. It also explained, as a natural consequence rather than a coincidence, a long-known relationship between how bright a spiral galaxy is and how fast it spins a tight, clean correlation that, in the dark matter picture, has to be put in somewhat by hand, but which falls straight out of Milgrom's formula. For predicting the behavior of individual galaxies, MOND is, frankly, very good. It is good enough that it cannot be honestly dismissed, and the people who have pursued it for 40 years have not been fools. They have been holding on to something that genuinely captures a pattern in the data. In fact, the pattern is sharper than even its supporters first realized, and it is the single best card MOND holds, so it deserves to be laid on the table plainly. When astronomers gathered together a large, careful sample of galaxies of every kind, big and small, bright and faint, gas-rich and gas-poor, and asked a simple question of each, the answer was uncomfortably clean. The question was this: at any given point in a galaxy, take the gravity you would predict from the visible matter alone, and compare it to the gravity the stars actually feel. In the dark matter picture, the relationship between those two numbers should be loose and scattered, because every galaxy has its own particular dark halo, with its own shape and size layered on top of the visible matter in its own way. There is no reason the visible matter alone should predict the total gravity, and yet it does. Across the whole sample, the gravity the stars feel is tied to the gravity from the visible matter by a single tight relationship, with almost no scatter, as though the visible matter alone somehow dictates the total pull, dark halo and all. That is exactly what MOND predicts and exactly what the dark matter picture finds awkward. It does not prove modified gravity. Defenders of dark matter argue that the relationship emerges from the orderly way halos and galaxies grow together. But it is a real, sharp, unexplained regularity, and it is the reason serious people have never been willing to write MOND off entirely. But a theory of gravity does not only have to explain galaxies, it has to explain everything gravity does, on every scale. And this is where MOND has run into trouble. It has never fully escaped. The first and deepest trouble is the oldest light, the cosmic microwave background. That afterglow of the early universe carries within it a detailed pattern, a series of peaks and ripples in how its temperature varies across the sky. And that pattern is exquisitely sensitive to what the universe was made of when the light was released. The dark matter picture predicts that pattern with extraordinary precision. You can compute it from the theory and overlay it on the measurement and watch them match, peak for peak. MOND, with no dark matter to work with, has never been able to reproduce that pattern in a convincing way. The early universe seems to have contained a component that gravitated, but did not interact with light, which is to say, it seems to have contained dark matter, and the imprint of that component is written across the whole sky. The second trouble is the growth of cosmic structure. We saw how dark matter, falling together early and unopposed, dug the wells that everything else later poured into. That early head start is what gave the universe enough time to build the great web of galaxies we actually see. Without a dark component to collapse ahead of the ordinary matter, structure forms too slowly and too smoothly. The rich, clumpy cosmic web becomes hard to assemble in the time available. The same head start that the dark matter picture provides naturally, MOND struggles to provide at all. And the third trouble is the one we already walked through, the bullet cluster, where the mass and the gas come apart, and the gravity follows the mass out to where the nearly empty galaxies are, not the gas where most of the ordinary matter sits. For a theory whose entire premise is that gravity is generated by visible matter, a place where the gravity plainly is not coming from the visible matter is a deep wound. The MOND community has not been idle in the face of all this. The original idea has been extended, made consistent with relativity, dressed in more sophisticated mathematics, patched and elaborated to try to meet these challenges. Some versions get partway, but none has yet matched. With a single coherent framework, everything the dark matter picture handles at once, the galaxies and the cosmic background, and the growth of structure, and the colliding clusters, all together from one set of rules. The patches that let MOND survive in one arena tend to weaken its elegance in another, and elegance and economy were the whole point. There have even been attempts to test the idea much closer to home, on the smallest systems where its gentle gravity threshold could possibly bite. Out in our own galactic neighbourhood, there are pairs of stars orbiting each other at enormous separations, so far apart that the pull between them dips below Milgrom's threshold, into the regime where his modified gravity is supposed to take over. In ordinary gravity, those widely separated partners should drift around each other at one speed. Under MOND, they should move detectably faster. Astronomers have begun measuring such pairs in large numbers, hoping to catch gravity in the act of breaking Newton's rule right here in the Milky Way, with no dark matter involved at all. The results so far are tangled and disputed. Some teams report a hint of the MOND effect, others report none, and the measurement is fiendishly hard, because you have to be sure the two stars are truly bound and truly alone, with no hidden third companion skewing the motion. It is not settled, but it is a striking thing that the question of whether gravity itself misbehaves can now be put, in principle, to a pair of stars you could point a backyard telescope toward, and the evidence has kept arriving on the dark matter side. In 2025, a team led by the astronomer Mariana Giulio, working at an institute in Potsdam, in Germany, with collaborators including Justin Reed at the University of Surrey, looked at some of the faintest, smallest galaxies known, the ultra-faint dwarf galaxies, tiny scattered handfuls of stars that orbit our own Milky Way. These are, in the dark matter picture, the most dark matter-dominated objects in the universe, dwarf wisps of starlight buried in disproportionately huge halos of the invisible. The team measured how the stars in these dwarfs move not just their overall motion, but how the pull on them changes from the center of the dwarf to its edge, and compared what they found against detailed simulations. The result came down clearly on one side. The gravity inside these little galaxies could not be accounted for by their visible stars alone, at any radius. There was, in the language of the work, missing information, a hidden component shaping the motion that the visible matter simply did not contain, a halo of dark matter, encoding that missing information fit the data. The requirement at the core of MOND, that the gravity be fixed entirely by what we can see, did not. As Red put it, the smallest galaxies seem to be telling us that what we can see is not enough to determine the pull their stars feel. Something invisible is carrying the rest. For the kinds of MOND proposed so far, he said, that just does not seem to work. None of this is a funeral. Tom, MOND has not been killed outright, and good scientists still take it seriously, partly because its successes with individual galaxies are real and genuinely unexplained on the dark matter side. There are patterns in galaxy rotation so tight and so simple that MOND predicts them effortlessly in the dark matter. Picture has to work to match. A complete theory will have to account for why MOND works as well as it does, even if dark matter is real. But the weight of the whole body of evidence, taken together the oldest light, the growing web, the colliding clusters, the smallest galaxies, has been pressing steadily against modified gravity as a complete replacement for dark matter, and pressing harder every year. So we arrive at the uncomfortable center of the whole problem. The gravity is undeniably there. The universe behaves, on every scale, as though it is full of unseen mass. The most natural particle to supply that mass has not shown up after 40 years of the most sensitive searching ever attempted, and the most serious attempt to do without a particle altogether, by changing gravity instead, cannot cover all the ground that dark matter covers. We are quite sure something is there. We have ruled out the easiest answer to what it is, and we have ruled out the easiest way of saying it is nothing at all. This is the honest shape of the field today, and it is worth stating plainly rather than dressing up. After 90 years, two of the most appealing complete answers have both been found wanting, not refuted outright, but worn down, hemmed in, deprived of the easy victory each once seemed close to. The particle physicist's favourite has not appeared in the detectors built for it. The alternative theorist's favourite cannot stretch to cover the early universe and the colliding clusters at once. And yet the evidence that something is there has only grown stronger over those same 90 years, from a single contested cluster to an overwhelming, cross-checked, many-angled certainty. We have never been more sure that the dark matter is real, and we have rarely felt further from knowing what it is. Those two facts, held together, are the strange and honest centre of the whole subject. It is not a comfortable place, but it is a real one, and it is where the science actually stands tonight, beneath all the speculation, which leaves the field wide open and, in a way, more interesting than it has been in decades. If the dark matter is not a WIMP, then it is something else, and there is no shortage of candidates. Some of them are very light, far lighter than anything the xenon detectors were tuned to feel. Some of them are not particles in the ordinary sense at all, and at least one of them is an idea so old it predates the whole modern hunt, brought back to life by the detection of ripples in space itself. If dark matter is not the heavy sluggish WIMP, the next most serious candidate is almost its opposite, a particle so light it is nearly nothing at all. It is called the Axion, and the most appealing thing about it is that, like the WIMP before it, it was not invented to explain dark matter. It was invented to fix something else, and the fact that it might also solve the dark matter problem came as an unexpected bonus. There is a freedom in this moment of the story that is easy to miss under the disappointment. For 40 years, the field leaned so heavily on the WIMP that other ideas struggled for attention and funding. The obvious answer crowded out the strange ones. The silence from the deep detectors, frustrating as it is, has had one healthy effect: it has thrown the question back open. With the favourite no longer obviously right, physicists have gone back to taking the alternatives seriously, dusting off candidates that had been waiting in the wings for decades and inventing new ones. The mass range of possible dark matter particles that people now consider plausible spans an almost incomprehensible stretch, from things far lighter than a neutrino to things as heavy as a small mountain. We do not merely lack the answer. We do not yet know within many orders of magnitude how heavy the answer is. That sounds like ignorance, and it is. But it is also a kind of opening. The truth is still out there in that vast range, and the narrowing has only just begun. The something else is a small nagging puzzle in the physics of the strong nuclear force. The force that binds quarks together inside protons and neutrons. By every right, that force ought to behave slightly differently depending on a kind of mirror reversal of nature. It ought to show a small lopsidedness. But it does not. As far as anyone can measure, It is perfectly balanced, far more perfectly than it has any obvious reason to be. In the late 1970s, physicists proposed a clever fix for this. A new field spread through all of space that would naturally and automatically tune that lopsidedness down to zero, and a consequence of that field falling out of the mathematics was a new particle. It was Frank Wilczek and Steven Weinberg who gave it a name, and Wilczek, with a certain lightness, named it after a brand of laundry detergent because it cleaned up the problem. The axion, if it exists, would be staggeringly light and many trillions of times lighter than an electron, and it would have been produced in great abundance in the early universe. Being so light and so reluctant to interact, it would drift through the cosmos cold and slow and invisible, exactly the way dark matter is supposed to. If the universe is full of axions, there are not billions of them passing through you each second, but something almost beyond counting, a dense, ghostly field of them everywhere, oscillating very slowly, far too gently to feel. Catching an axion requires a completely different kind of trap than catching a WIMP. You cannot wait for it to strike a nucleus. It is far too light to leave that kind of mark. But an axion in a strong magnetic field should very occasionally convert into a faint particle of light, a photon of a very particular frequency that depends on the axion's mass. So the experiments built to hunt for it are not tanks of xenon in the dark. They are exquisitely tuned chambers sitting inside powerful magnets, slowly sweeping across a range of frequencies, like someone turning the dial of a radio with infinite patience, listening for the one faint station that would be the universe's axions, singing themselves into light. A dedicated experiment in the United States has been turning that dial for years, narrowing the search. The axion has not yet answered. But unlike the WIMP, its most promising hiding places have not all been emptied out, and many physicists now consider it the leading candidate, the most natural place for the answer to be. The reason the axion inspires such loyalty is the same reason the WIMP once did, and then some. It is not a desperate patch. It was proposed to solve a real and independent problem, and it would, if it exists, kill two mysteries with one particle fixing the strange perfect balance in the strong nuclear force and supplying the dark matter at the same time for free. A particle that solves two unrelated puzzles at once has a kind of credibility that a particle invented to solve only one never quite earns, and the search for it is now entering its most sensitive phase, with new experiments using larger magnets, colder chambers, and clever quantum tricks to listen for that faint conversion across an ever wider band of possible masses. There is a real chance, not a certainty, but a real chance that within the coming years one of these dials will land on the right frequency, and a faint hum will rise out of the noise, and the dark matter will turn out to have been an almost weightless particle named, half as a joke, after a box of detergent. It would be one of the strangest vindications in the history of physics. There are others. One is the sterile neutrino. Ordinary neutrinos are already among the strangest things in physics, nearly massless, almost untouchable, pouring through the universe in unimaginable numbers. A sterile neutrino would be a heavier, even more aloof cousin, one that does not feel even the weak nuclear force that lets ordinary neutrinos occasionally interact. It would touch the rest of the universe through gravity alone, which makes it a natural dark matter candidate. A sterile neutrino of the right mass would, very slowly, decay, and when it did, it should give off a faint glow of X-rays at one sharp, specific energy. A few years ago, astronomers thought they might have glimpsed exactly such a glow, an unexplained line in the X-ray light from clusters of galaxies, sitting at an energy where no ordinary atom was expected to emit. For a while, it was one of the most tantalizing hints in the field, but it has proved frustratingly hard to confirm. Other observations have failed to find it where it should have been, and the signal has faded into dispute rather than discovery. The sterile neutrino remains possible and unproven. The story of that faint X-ray line is a small parable of how this whole field tends to go, and it is worth telling because the same shape recurs again and again. Two separate teams, looking independently at the combined X-ray glow of many galaxy clusters, reported a weak excess at one particular energy, just the kind of thing a decaying sterile neutrino would produce. It was faint, but it was there in more than one place, which is exactly what makes a hint feel real. Excitement followed. Then came the harder work of checking. Other groups pointed their X-ray telescopes at objects where the line should have been even clearer at nearby dwarf galaxies dominated by dark matter, where there is little else to confuse the signal, and found nothing at the expected strength. Some argued the original excess could be explained more mundanely by ordinary atoms in the hot cluster gas, emitting at a nearby energy that had been overlooked. The hint did not so much die as dissolve, leaving the community divided and the question open. It is a pattern you learn to recognize in the dark matter search. A faint signal, a flush of hope, a long grind of scrutiny, and finally not an answer but a more carefully drawn map of where the answer is not. And then there is the strange and beautiful idea of dark matter so light that it stops behaving like a collection of particles at all. If the dark matter were ultralight lighter even than the axion, by an almost absurd margin, then the quantum nature of matter would assert itself on a cosmic scale. Every particle in nature has a wavelength, a fuzziness, that grows as the particle gets lighter. For ordinary matter, it is far too small to notice, but for dark matter, that wavelength could swell to the size of a whole small galaxy. The dark matter would then behave less like a swarm of tiny bullets and more like a single vast standing wave, a cosmic ripple lapping through space, smoothing out the smallest structures and softening the dense cores of galaxies. This idea, sometimes called fuzzy dark matter, is attractive partly because it might fix some small, nagging discrepancies between what the cold dark matter simulations predict on tiny scales and what we actually see in the smallest galaxies. It remains speculative, but it is a reminder of how wide open the question still is, that the missing mass of the universe might turn out to be a substance so ghostly and so light that a single particle of it, smeared into a wave, would be larger than the galaxy it helps to hold together. And then there is the oldest and perhaps the strangest candidate of all, the idea that the dark matter is not a new kind of particle at all, but a vast population of black holes, made in the first instance after the Big Bang. Ordinary black holes form when massive stars die and collapse, but primordial black holes, if they exist, would have formed long before any star in the first fraction of a second of the universe's life, when the cosmos was so dense that regions of it could have collapsed directly into black holes on their own. Such objects would be black, of course, and they would gravitate, and a swarm of them drifting through the galaxy would behave, from a distance, very much like dark matter. The idea had been around for decades as a quiet possibility. Then, in 2015, the gravitational wave detectors known as LIGO heard for the first time the faint chirp of two black holes spiraling together and merging 1 billion light-years away, and some of those black holes turned out to be a little heavier than astronomers had expected, stellar deaths to easily produce. That raised an old question with new force. Could some of these be primordial relics, not of dead stars, but of the Big Bang itself? And could there be enough of them to be the dark matter? The honest answer is, probably not all of it, but the door is not fully shut. Black holes, even dark ones, are not perfectly invisible. A black hole drifting in front of a distant star would, for a moment, bend and brighten that star's light by its gravity, a brief gravitational flicker called microlensing. And astronomers have watched millions of stars for years, looking for exactly those flickers. The number they find puts hard limits on how many black holes of various masses can be hiding out there. Across most ranges of mass, there are simply not enough flickers. Primordial black holes cannot be the bulk of the dark matter at those weights, but there remains a narrow window at around the mass of a large asteroid, where the objects would be too small to cause a catchable flicker and too large to evaporate away, where a population of tiny ancient black holes could, in principle, still be hiding. It is a strange thought to fall asleep to, that the missing mass of the universe might be countless black holes the size of mountains, made before there were stars, drifting unseen through the spaces between them. The hunt for these flickers has become its own quiet epic. One survey trained a powerful telescope on the Andromeda galaxy for a single long night and captured tens of millions of its stars at once, watching for the briefest brightening that a passing dark object would cause. Across all those millions of stars and all those hours, it found almost nothing, a near total absence of flickers that slammed the door on whole ranges of possible black hole masses. Ruling out the idea that objects of those weights could make up the dark matter, other long campaigns, Monitoring the dense star fields toward the center of our own galaxy and toward its small satellite galaxies have tightened the limits further. Out of all of this, the asteroid mass window survives, narrow but real, simply because objects that small pass too quickly and bend too little to leave a flicker we can yet catch. It is a humbling kind of result. We have not found the black holes, but we have not been able to fully rule them out either. In that one stubborn gap, the dark matter might still be there, in pieces too small to flicker and too quiet to find. There are stranger possibilities, still whole hidden families of dark particles with their own dark forces, a shadow physics that touches ours only through gravity, mirroring the richness of ordinary matter in a sector we can never see. Most of these will turn out to be wrong. That is how it goes. The universe entertains far fewer possibilities than theorists propose, but one of them, or something no one has yet thought of, is presumably the truth, drifting through the dark room right now, waiting for an experiment clever enough to feel it. And here, just as the particle hunt was settling into its long, patient grind, the universe chose to make the whole problem larger, because in the last few years, it has become clear that dark matter is not the only thing in cosmology that has stopped behaving. The cracks have started spreading into the model itself. The very framework we use to fit the dark matter into the standard story of how the universe expands and grows has begun, quietly, to come apart. For most of the last few decades, there was a comforting sense that cosmology was nearly finished, that the big picture was settled, the proportions measured, and only the details remained. The dark matter and dark energy were unexplained, yes, but they sat in a framework that otherwise fit the data with almost embarrassing precision, and the working assumption was that the names would eventually be filled in without disturbing the rest. That comfortable sense has been eroding. One by one, measurements that were supposed to lock into place have instead refused to agree, and the refusals have not gone away with better data they have sharpened. It is no longer obvious that the missing pieces can simply be slotted into the existing picture. It is starting to look possible that fitting them in will require changing the picture. And so the dark matter, which began as a single anomaly in a single cluster, has come to feel less like a gap in an otherwise complete map, and more like the loose corner of something larger, which, if you pulled on it, might lift away to reveal that the map was never quite the shape we thought. The first crack is in the simplest number you can ask about the universe. How fast is it expanding? There are two good ways to measure that rate, and the trouble is that they no longer agree. The first way looks deep into the past, at the oldest light, the cosmic microwave background. From the detailed pattern frozen into that ancient glow and the well-tested physics of the early universe, you can calculate how fast the cosmos should be expanding today. The second way is more direct and more local. You build a ladder of distance measurements, rung by rung, starting with certain stars in nearby galaxies whose true brightness we know, stepping out to more distant exploding stars, and from how those distances relate to how fast the galaxies are receding, you read the expansion rate off the nearby universe directly. Both methods are mature. Both have been refined for years by careful people who have hunted relentlessly for their own mistakes, and they give different answers. The local measurement comes out meaningfully faster than the early universe prediction, not by a wild amount, but by a gap that has stubbornly refused to close as the measurements have sharpened. When two careful measurements of the same quantity disagree, and keep disagreeing even as both grow more precise, that is not a comfortable situation. It usually means that one of them hides an error no one has found, or that the model connecting the early universe to the late one is missing something. This disagreement has a name now, the Hubble tension, and it has gone from a curiosity that might wash out to one of the sharpest open problems in the field, a place where the standard story seems genuinely to strain. For years, the comfortable hope was that the tension would simply evaporate, that someone would find a flaw in the rungs of the local distance ladder, a miscalibrated star, an overlooked bias, and the two numbers would slide back into agreement. That hope has not been rewarded. The local measurement has been checked and rechecked, the distance ladder rebuilt with new and independent rungs, the nearby exploding stars recalibrated against fresh data from the most powerful telescopes, and the gap has not closed. If anything, it has firmed up, which has pushed more and more cosmologists toward the uncomfortable other possibility, that the measurements are both right, and it is the model in between that is wrong. To make the early universe prediction match the local one, you have to add something new to the recipe of the cosmos, Some extra ingredient in the first moments, some new kind of energy that briefly altered the expansion early on, or some unexpected property of the dark sector. None of the proposed fixes is clean, and none has won the field over. But the very fact that resolving a simple disagreement about a single number may require inventing new physics tells you how deep the crack might run. The dark matter and dark energy were already two enormous unknowns sitting at the heart of the model. The Hubble tension hints that the way they fit together over cosmic time may itself be incomplete. The second crack runs through the larger and stranger of the two dark components, dark energy, the thing driving the expansion to speed up rather than slow down. For a long time, the simplest assumption held, that dark energy is a constant, an unchanging tension built into empty space itself, the same yesterday and today and a billion years from now. That assumption is the backbone of the standard model of cosmology. But a great survey now underway, mapping millions of galaxies across the sky to chart the history of the expansion in fine detail, has begun to find hints that dark energy may not be constant after all. The data, as it has accumulated over the last couple of years, leans towards something unsettling, that dark energy was slightly different in the past than it is now, that it has been changing, weakening, evolving over cosmic time. The finding is not yet beyond all doubt. This is exactly the kind of claim that demands more data and harder scrutiny, and it is getting both. But if it holds, it would mean that the largest component of the universe is not a fixed feature of space, but a thing with a history, a process, rather than a constant, something that is still going on. Sit with that for a moment, because it changes the texture of the whole picture. We have spent a century treating the universe as a machine governed by fixed laws and fixed constants, and reading those constants off the sky. The hint from these surveys is that one of the most important of them may not be a constant at all. The framework was built to describe a static set of rules. The thing it is describing may be in motion. The way this measurement is made, is itself worth dwelling on, because it shows how far the craft has come. The survey takes the light of millions upon millions of galaxies and quasars, spread across billions of years of cosmic history, and uses them to trace that frozen sound wave ruler, the same standing ripple laid down in the early plasma, at many different distances, and therefore at many different ages of the universe. By watching how the apparent size of that ruler changes as you look further and further back, the survey reconstructs the entire expansion history of the cosmos, epoch by epoch. And when the most recent data is laid against the simplest model, the one with unchanging dark energy, it does not quite fit. The preference that emerges is faint but persistent, and it points the same unsettling way, that the push of dark energy was a little stronger in the past and has been easing since. The result is not yet certain enough to overturn the textbooks. Extraordinary claims demand more, and the teams involved are the first to say so. More data is coming, from this survey and others, and it will either harden the hint into a discovery or melt it back into noise. But the mere fact that the largest and most carefully gathered map of the universe ever made leans even slightly toward an evolving dark energy is enough to have unsettled the field. The backbone of the standard model is being asked, gently but seriously, whether it is really a backbone at all. And then there is the third crack, the one that arrived from the most powerful telescope ever flown, looking further back than anything before it. The James Webb Space Telescope was launched at the very end of 2021, a folded mirror 6.5 meters across that unfurled 1.5 million kilometers from Earth and began collecting the faint infrared light of the most distant, most ancient objects in the universe. It was built, among other things, to see the first galaxies, to look back into the era astronomers call the Cosmic Dawn, the first few 100 million years after the Big Bang, when the very first structures were supposed to be flickering into being, and the expectation was clear. Back then, so early, the galaxies should be small, faint, ragged, half-formed little knots of gas just beginning to assemble, the rough first drafts of the grand galaxies that would take billions of years to grow. That is not what the Webb telescope found. It found galaxies that were already there, too big, too bright, too finished, too soon. One in particular has become the emblem of the puzzle. Its catalogue name is long, but what matters is its distance. It is seen as it was when the universe was less than 300 million years old, a mere 2% of its present age, and it is not a ragged wisp. It is a substantial galaxy, holding hundreds of millions of suns worth of stars, far brighter and more developed than anything the models said should exist that early. And then follow-up observations found something even harder to swallow inside it: oxygen. Oxygen matters here because of where it comes from. The early universe, fresh out of the Big Bang, contained essentially only the lightest elements: hydrogen and helium and a trace of lithium. Every heavier element, all the oxygen and carbon and iron in existence, had to be forged later, inside stars, by the fusion that powers them, and then scattered back into space when those stars died, often in supernova explosions, seeding the next generation. Oxygen is built in the hearts of massive stars and flung out when they explode. To have a galaxy already enriched with oxygen, you need a whole prior generation of massive stars to have lived their entire lives, run through their fuel, and died. And massive stars live fast, but not instantly. To find a galaxy that early already salted with oxygen means that an even earlier generation of stars had already been born, burned, and died inside it, all in a window of time that the standard picture says was barely long enough to make the galaxy at all, let alone age it. It has been likened, with some justice, to walking into a delivery room moments after a birth and finding not a newborn, but a grown adult fully formed, where there should not yet have been time to form anything. And this galaxy is not alone. The Webb telescope has now found a whole population of these early galaxies, far more numerous and more massive than anyone predicted, lighting up the cosmic dawn that was supposed to be dim and empty. The Dark Ages, it turns out, were not so dark. No one yet knows what this means. Perhaps the first stars were larger and more efficient at building galaxies than we thought. Perhaps the early dark matter halos pulled their gas together faster than the simulations expected. Perhaps something in the timeline itself is off. The explanations on offer all require changing some assumption we had been comfortable with, and none of them yet fits cleanly. The data is ahead of the theory. The universe built its first galaxies faster than our best model says it could, and the model has not yet caught up. Each candidate explanation is interesting in its own right, and each has a cost. Maybe the very first generation of stars was monstrous stars, hundreds of times the mass of the Sun, blazing far brighter per unit of matter than any star today, so that a young galaxy could shine like a finished one while still being lightweight. Maybe early star formation was simply more efficient, turning a larger fraction of available gas into stars before the usual processes could blow that gas away. Maybe the galaxies only look too bright because we are misreading their light, mistaking the glare of feeding black holes at their centers for the glow of stars. Or maybe, and this is the possibility that touches our story most directly, the dark matter halos in the early universe were denser, or assembled sooner than the standard cold picture predicts, giving the gas deeper wells to fall into and a head start on building galaxies. Notice that nearly every one of these roads leads back to the dark matter, because the dark matter set the stage on which the first galaxies formed. If the galaxies grew too fast, one natural suspect is the scaffolding they grew on. The early universe puzzle and the dark matter puzzle may not be two separate mysteries at all. They may be the same mystery, seen from two different distances in time. There are even hints contested, unproven but persistent, that the universe may not be as featureless and even-handed as cosmology has always assumed. The foundational principle of the whole field is that the cosmos has no center and no preferred direction, that it looks essentially the same everywhere and every way you turn, on the largest scales. Yet certain patterns in the oldest light seem, oddly, to line up with one another along a particular direction, when they ought to be randomly oriented in alignment that picked up the only half-joking nickname the axis of evil. And astronomers have reported enormous arcs and rings of galaxies, structures stretching across billions of light years, far larger than the standard picture says any structure should be able to grow. These claims are genuinely disputed. Some careful analyses argue the patterns are flukes, the kind of accidental alignment a large enough sky will always throw up somewhere, and the matter is not settled, but they sit in the same growing pile as the rest small, stubborn signs that the tidy model has loose threads, and that pulling on any of them might unravel more than we expect. It is important to be careful here, because this is exactly the territory where the human mind is most easily fooled. We are pattern-finding creatures. Show us a wide enough field of random noise, and we will pick out faces, arcs, alignments, meaning, A great deal of the work in modern cosmology is the unglamorous labour of asking, again and again, whether a striking pattern is really there or whether it is the kind of coincidence that becomes inevitable once you search a large enough sky. Most of these anomalies may yet dissolve under that scrutiny, as the faint X-ray line dissolved as so many hints have dissolved before. None of them, on its own, is anything like proof, but the reason they are worth mentioning at all is the company they keep. A single odd alignment in the early light would be a curiosity to be explained away. A whole collection of separate strains, the expansion rate that will not settle, the dark energy that may be drifting, the galaxies that grew too fast, the faint suggestions of a preferred direction arriving together in the same decade from different instruments and different teams is harder to wave off. It may be that each one resolves on its own and the standard model emerges intact, or it may be that they are not separate at all, but different surface cracks over the same deep fault, and that the fault has the dark sector running straight through it. None of these cracks, on its own, is a catastrophe. The standard model of cosmology is not collapsing. It remains by a wide margin the best account of the universe we have ever had, and it still passes test after test that nothing else can. But the cracks are real, and they are multiplying, and they have something in common: the expansion that will not settle on one rate, the dark energy that may not be constant, the galaxies that grew up too fast. Each one is a place where the universe is doing something the model did not lead us to expect, and the dark matter, the original unknown, sits at the centre of all of it, the largest piece of the puzzle whose shape we still cannot see. There is a way of seeing this moment not as a failure but as a familiar kind of threshold. Physics has been here before. At the close of the 19th century, there were a couple of small, stubborn discrepancies that the magnificent physics of the day could not quite explain: a problem with the glow of hot objects, a puzzle about the speed of light. They looked like minor cleanup, loose ends to be tidied. Instead, they cracked open into quantum mechanics and relativity, and the whole edifice of physics was rebuilt around them. No one living through it knew, at first, that the small anomalies were doorways. They looked like nuisances. It is at least possible that the dark matter, and the cracks now spreading out from it, are doorways of the same kind that the inability to find the missing mass, and the strains showing up alongside it, are not gaps to be filled within the current picture, but signs that the picture itself is due to be redrawn. We cannot know that yet. Most anomalies are just anomalies, but the largest unsolved problem in physics has a way of being more than it appears, and the people working on it are aware, in their more honest moments, that they may be standing closer to a threshold than to a solution. It is tempting, at a moment like this, to reach for something grand, to say that everything we knew is wrong, that physics is in ruins, that reality has been overturned. That would be false, and it would also miss what is actually interesting. Nothing has been overturned. What has happened is quieter and harder. We have arrived, with enormous effort, at a clear and honest map of the edge of our knowledge, and the edge is closer in, and stranger, than we had let ourselves believe. We have learned, with great precision, the exact shape of what we do not understand. And so, after 90 years, we come back to the room. It is dark. The walls are solid. The air is still. You are lying in the quiet, perhaps closer to sleep now than when we began, and the particles are still passing through you, the same particles that were passing through you when this started, and through Zwicky on his mountain, and through Rubin at her telescope, and through every detector lowered into every mine. They have not changed. They never announced themselves. They were here the whole time, in their billions, crossing your body every second, and you have felt nothing, because there is nothing to feel. They are the same stuff that fell together first in the early dark, and dug the wells that the galaxies poured into, the same stuff that holds the spinning galaxies from flying apart, and bends the light of distant quasars into doubled images, and sailed clean through the wreck of the bullet cluster while the gas piled up behind. The same stuff our most sensitive instruments, 3 million times keener than when the search began, have waited years to catch and have not caught. It built the place. It is most of the matter there is. It is inside you now, and we do not know what it is. That is not a failure, and it is not a tragedy. It is simply where we are. We know where the dark matter is, on every scale, from the halo around a dwarf galaxy to the web that spans the observable universe. We know how much of it there is, to within a few percent. We know, in remarkable detail, what it does and what it has done. We have ruled out the answer we were most sure of, and most of the easy ways around it, and that ruling out is itself a hard-won kind of knowledge, a clearing of the ground, so that whatever is really there has fewer places left to hide. Fritz Zwicky saw the first sign of it in 1933 and was largely ignored. Vera Rubin saw it again, plainly, in the spinning of galaxies, and reported it without raising her voice. The detectors are still in their minds, still waiting. The great surveys are still mapping the invisible web across the sky. Somewhere, a chamber inside a magnet is still turning its dial slowly through the frequencies, listening for a faint particle of light that has not yet come. We are still looking. That is the truest thing that can be said tonight. Not that we have the answer, but that the question is still open, and that people are still, patiently, in the dark, trying to feel for the shape of it. The dark matter is in the room with you. It always has been. It asks nothing and explains nothing. It simply is most of the matter in the universe, drifting through you at this very moment, holding the galaxies together out beyond the window, and keeping its single oldest secret a little longer. We know where it is. We do not yet know what it is. Good night.